Good morning. Today's lecture will continue on canonical forms. Last lecture I already explained about the canonical and the dual canonical forms. Basically, it's based on sum of products or products of sum. In summary, product of sum, which is the canonical form, used to be each term, multiplication of different terms plus, or actually, let's talk about sum of products. Okay, let me bring up pen, I'm sorry. Sum of products, which is the canonical form. It will be, if it is, for example, three variables multiplied with each other, which means they are in AND gates. Then there is one in OR, here is AND gates. So the total, they will be added together in one OR. So that's what we see here. AND gates, and there is one OR. This is sum of product, which is the canonical form. However, there is a dual form. So in the duality, every AND will be OR, every OR will be AND. This means any multiplication will be addition, any addition will be multiplication, any 1 will be 0, any 0 will be 1. That's the duality. So here, instead of dealing with each term has the three variables, in the duality the term will be ORed, or they will be ORs, like they will be added together. So if there was three variables, there will be variable A plus B plus C times, for example, A bar plus B bar plus C bar, and so on. So also in the canonical form, when we do the table, we used to make as min terms as lower cases, while for the dual canonical forms, we used to deal with, we call it max terms. So in canonical form, for example, when we have 101, so this is equivalent to M5. So 101, we will say that whenever there is 1, we used to put the number without bars. When there is 0, we will put bars, B bar, then here is 1C. While in max terms, if it is, it will be the opposites. So it will be, instead of 1, it will be A, instead of at 1, instead of not being bar, it will be bars. And there will be addition plus B plus C bars. Okay? So just a quick review. When we have, let's assume M4 as min terms. It is actually in binary 1, 0, 0. And let's assume the variables A, B, C. It will be A, B bar, C bar. But when we deal with M4 as max terms, M4 is still 1, 0, 0. But it will be, in terms of A, B, C, it will be A bar plus B plus C. How we get this? You can apply the duality for these parts. The duality for this, it will be A bar plus B plus C. That's how we can get this. In min terms, whenever we deal with the variables, let's assume that we have a variable A, B plus A bar, B bar, C. We need to make it in the general formula such that each term must include three variables. What do we need to do? We used to make it A, B, and the missing variable is C. Then we say AB plus 1 plus A bar, B bar, C. Then AB times C plus C bar, because C plus C bar equal to 1, plus A bar, B bar, C. Therefore, it will be ABC plus A, B, C bar plus A bar, B bar, C. Then we can say it's actually, this is 0, 0. I'm sorry, this is actually 1, 1, 1. This is 1, 1, 0. This is 0, 0, 1. This is equivalent to M1. This is equivalent to M6. This is equivalent to M7. Then we can say as a result, it's the sum of M1, 6, 7. This is in terms of min, if we are dealing with min terms. If we need to deal with max terms, it's pi and make M as uppercase, then make the complement. So we know for 3 variables we have the range from 1 to 7, 0 to 7. Then 0 is not included here, then 0 put it here. 1 is included, then don't enter it. 2 is not, then 2. 3 is not included, then put 3. 4 is not included, put 4. 5, 6 is included, 7 is included, then we are done. That's how we find the max terms. After that, if we need to calculate it as a functions, so the same function, if we need to convert this as a max terms, it will be as, we can make it like m0 plus m2 plus m3 plus, times m2 times m3. Let me erase it and rewrite it. It's times, it's not multiple. m0, because multiplication, times m2 times m3 times m4 times m5. Then we can say that 0 is actually 0, 0, 0. 1 or 2 is actually 0, 1, 0. 3 is 0, 1, 1. 4 is 1, 0, 0. 5, 1, 0, 1. Then we can say that 0, 0, 0 is actually equivalent to A plus B plus C times 0, 1, 0 is actually equivalent to A plus B bar plus C. Then times 0, 1, 1 is actually A plus B bar plus C bar. Then 1, 0, 0 is actually equivalent to A bar plus B plus C. This is times. Then times 101 is equivalent to A bar plus B plus C bar. Okay? Does this make sense? Again, here's 0, 0. Because here we have 0, 0, 0. This is 0, 1, 0. This is 0, 1, 1. This is 1, 0, 0. This is 1, 0, 1. That's why we get it. Okay? Remember, the max terms, 1 means because we are dealing with the complements. So that's how we can represent this also in terms of max terms. If we need to represent this in truth table, we can make it as shown here. Here is A, B, C, then 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So here is the function f. If we need to mention about min terms or max terms, in terms of min terms, this is m0, this is m1, here is m2, here is m3, m4, m5, m6, m7. Okay. Then in terms of max terms, this is m0, this is m1, m2, m3, m4, m5, m6, m7. So the location of min terms and the location of max terms are the same. So now, what else? How can I represent f as min terms? F, let me make it here, min terms. Min terms are basically the location of ones. So in min terms, f equal to 1, 6, 7, right? So in min terms, I'm going to put it here. At 1, here is 1. 6, here is 6, 7. So the remaining are zeros. 0, 0, 0, 0, 0. Do you agree with me on this? Okay. Now how about max terms? F as max terms. F as max terms will give you the location of zeros. So in min terms it was location of ones, while max terms, because it's the opposite, it will be the location of zeros. Location of zeros. So let's look at the max terms. We already got them here. 0, 2, 3, 4, 5. So we will apply it here, but keep in mind this is our location of zeros. Locations of zeros. So by looking at this, it will be at 0 will be 0, at 2 will be 0, at 3 will be 0, 4, 0, 5, 0. So how about the remaining elements? The remaining elements will be ones. 1, 1, 1. So that's how we represent this. As a result, we can get this conclusion, which is, which color here? This conclusion, this the same as this one. They are the same. And that's right, that's normal, because it's the same function, but it depends on which representation I'm using. So as a result, we will realize that whenever I'm dealing with min terms, I'm giving the location of ones. Whenever I'm dealing with max terms, I'm giving the location of zeros. That's the same. So when you give the location of ones, the other parts, the default will be zeros. So I don't need to make min terms and max terms together. You can either use ones, use one of them. You can use the location of zeros or you can use the location of ones. It's up to you. So then as a result, we will realize that f is the same. Then min terms equals to max terms. I mean, the same way, equivalent to max terms. You can use one of them. You don't need to use both. Okay? Clear? Okay, again, like min term is the product of sum, which is there will be and variables, while the max terms is the sum of products. And min terms will give us the location of ones, max terms location of zeros. Keep this in mind. Then they are exactly the same. They are representing the same function, even if they will be different way. Okay, any questions about this? Okay, let's look at this example. Let's assume we have M1, 4, 5, 6, 7. This is given in min terms. Sometimes it can be given as different way, like it can be given as sum of M1, 4, 5, 6, 7. So both of them representations are the same. So if we need to manipulate this or represent this in terms of min terms, how to find the min terms? Look at the min terms here, 1, 4, 5, 6, 7. So the default to find the max terms, look at the other numbers that's between 0 to 7 that's not included in the min terms. So which are basically 0, 1 here, 2 is not here, 2, 3, 4, 5, 6 are already included. Okay? So in other words, this will be as M0 times M2 times M3. So min terms will give you the location of zeros. Location of ones. So at 1 will be 1, at 4 will be 1, 1, 2, 3, 4, here's 4, will be 1, at 5 will be 1, 6 will be 1, 7 will be 1. However, the min terms will give you the location of zeros. Here is 0, here is 0, 0, because at 0 will be 0, at 2 will be 0, at 3 will be 0. Okay? So in terms, here's the min terms. This is M0, M1, M2, M3, M4, M5, M6, M7. But keep in mind, the uppercase or the max terms are for the location of zeros, the lowercase or the min terms location of ones. So the same function, the sum of min terms, is the same as the sum or the product of max terms. Okay, another example. Given the following truth table, find the canonical form in sum of products. Find this sum of products. When you read the word sum of products, you need to understand this as min terms. And when you look at the words product of sum, the word product of sum, this means max term. You need to be aware of this. Okay, so how to figure it out? By looking at the truth table. Min terms for location of ones. Max terms, location of zeros. Look at the location of ones. So for regarding to the min terms, we have 1. Here is we have 1, we have 1, we have 1. Now in this truth table, whenever you see it like this, I recommend you to write like this: M0, M1, M2, M3, M4, M5, M6, and M7. So the ones are located at 1, 2, 4, and 6, right? So 1, 2, 4, and 6. Here is the sum of min terms 1, 2, 4, and 6. In other words, it will be as M1 plus M2 plus M4 plus M6. Now, in terms of ABC, we need to do the following simplification. So in terms of ABC, I don't have space here. I'm going to write it here. So we already agreed that F equals to M1 plus M2 plus M4. Okay, let me write it better way. F equals to M1 plus M2 plus M4 plus M6. 1 is equivalent to 0, 0, 1. 2 equivalent to 0, 1, 0. 4, 1, 0, 0. 6, 1, 1, 0. Then we can write the variables here. It will be here, since there is 0, and in min terms means 0 means bar. So it will be A bar, B bar, C plus A bar, B, C bar plus A, B bar, C bar plus A, B, C bar. Okay? Do you agree with me? Okay. So how about in max terms? In max terms, they are the location of zeros. So here is 0, 0, 0, 0. So in max terms, it will be the multiplication of max terms here. 0 located at 0, then at M3, then here is M5 and M7. 5 and 7. You can find it from the truth table, or you can find it from the complements of these parts. It's up to you. So 0, 3, 5, 7. In other words, it's going to be M1, M0 times M3 times M5 times M7. So how to simplify it? I'm going to simplify it here in terms of max terms. They are, as I mentioned here, let me write it as M0 times M3 times M5 times M7. Now, how to represent this? 0 is actually equivalent to 0, 0, 0. M3 is equivalent to 0, 1, 1. M5 equivalent to 1, 0, 1. And M7, 1, 1, 1. Now, in terms of max terms, make sure that the 0 will give us the non-bar, while 1 will give us bar. So it will be A plus B plus C times, here there is 0, A, there is 1, B bar, there is 1, C bar, times, here there is 1, A bar, plus 0 for B, then B, then if there is 1, there is so C bar, then times, here is A bar plus B bar plus C bar. Okay? So this is very important, and you will see it in the quiz, which will be on Friday. There will be a question similar to this. Find the min terms, find the max terms, convert min terms to max terms. So I'm giving you the question now. So please be aware how to use it. If you know how to use it, of course, you'll get 10 off in the quiz. It will be straightforward. Just make sure to understand how to do it. Yes?
Will any of the Boolean algebra be on the quiz?
I'm not sure, there might be the other half of it. It might be two halves, or there might be included. So, like the tables for the postulates and the theorems, you are not required to memorize it. So you need to know how to use it. So basically, if there will be some questions, you will see the tables on it. But most likely what I encourage you first, study for the canonical forms. After you finish this, study for the Boolean algebra. Okay, make your priority on this one. Like basically how to make the to find the min terms, the max terms, how to make the convergent. After that, go to Boolean algebra. Okay, so now we know how to make the convergent. We know those are for location of ones, the others are location for zeros, then that's it. So canonical forms are just a way to represent or to make any function, to make it as a unique. So when I use the Boolean algebra, maybe my simplification different than yours, different than anybody else. So, but when we use this representation, we have two ways to represent the zeros or to represent the ones. Then we can make sum products or product of sum. So we have two representations or two systems to convert this. So we can guarantee that my design, the same as yours, the same as anybody else, then we can, if we need to follow with your design, it will be easy to, for example, to diagonalize where is the problem or to make sure that everything looks fine. And so it will be easy to follow, even though sometimes using the canonical forms can cost more equipment than using the short forms or like the shortcut forms or any other forms. But again, we are trying to standardize our solutions, so we will not go to the Boolean algebra and dealing with these difficulties. Okay? So the shortened form, I already explained it during the slides. So we can make it as sum product or product of sum. So basically, if we have 1, 2, 4, 6, we can write it in this form. Then in order to find their equivalents, we know it's 3 variables, so 2 power 3 equal 8. Then our range between 0 to 7, therefore subtracts all of the numbers between 0 to 7 from this number. So you will see that 0 is not included, that's why we put it here. 1, 2 are included, 3 is not, then put 2, 3, 4 is here, 5, put it here, 6 is here, 7 is here. So the complements. That's how we figure out. Then we can add all of this. If we add all of this together, you will get it from 0 to 7. That's the range if we have 3 variables. How about if we have 4 variables, 2 power 4, then it's just 16. Then the range between 0 to 15. We have M0 up to M15. Then if we need to make some indications, keep in mind, you need to compare between 0 to 15. How about if we have 2 variables, 2 power 2, which will be 4, then we have from 0 to 3. Okay? Then look between these ranges. It's up to the function. So you need to be aware of how many variables do we have before doing your analysis. So maybe when you see this 1, 2, 4, 6, and if it's 4 variables, then make sure that the range will be between 0 to 15. How can you recognize that? Do I have 3 variables or 2 variables or 1 or something like that? Look at the function. Like here, it's f, a, b, c, 1, 2, 3, then that's how I know it's 3 variables. Or it will be given in the question like, you have 3 variables or you have 4 variables. So look, that's how we recognize this. Okay, let's look at this comparison between canonical forms. So we already discussed this a lot. Let's do it one more time or another time. So here, since we are in the canonical form, not the dual, which is the min terms, or we call it sum of products. So sum of products, the same as min terms. Well, the product of sum, the same as max terms. And this is the same as canonical form. This is the same as dual canonical form. So whenever you see any of these canonical form, any of these 3 definitions, should be the same. So basically, we can say this is 0, 0, 1, 0, 1, 0 because it's written in min terms. Then here 1, 0, 0. Here 1, 1, 0. Okay? Now 0, 0, 1 equivalent to 1. So this we call it M1. Then here plus 0, 1, 0 equivalent to 2. This is M2. Then 1, 0, 0 equivalent to 4. This is M4. 1, 1, 0 equivalent to 6. This is M6. So as a result, it will be sum of 1, 2, 4, and 6. We have 3 variables. 2 power 3, which is A. Then our range between 0 to 7. Look here. Compare the numbers between 0 to 7 here to convert it to max terms. 0 is not included. 1, 2. Then 3 is not included. 4 in here. 5 is not included. 6. Then 7. 0, 3, 5, 7. Then how to find it? 0 equivalent to 0, 0, 0. 3 equivalent to 0, 1, 1. 5 equivalent to 1, 0, 1. 7, 1, 1, 1. Here we are dealing with max terms. Then the 0 will be non-bar while 1 will be bar. So this will be in terms of A, let me write it in lowercase. It will be A plus B plus C. There is no bars because in the max terms, no bars at zeros. So here is A plus B bar plus C bar. Here is A bar plus B plus C bar. Here is A bar plus B bar plus C bar. Okay? Any question? Now let's look about, like, there's some things called standard form, there's something called canonical form. The standard form, which is the form that's written in short way. So in the standard form, not all variables will be appeared. So standard form, it looks like canonical form. But the difference is in the standard form, not all variables need to be appear. So sometimes the standard form can be written in short way, but not all variables. Which is, for example, this is FA bar B bar C plus AB plus C, this function. So look at this function, we will realize the first term written as 3 variables. Second term, only 2. Third term, only 2. Again, this term looks like sum of products because we have products plus products, or we have and then there is or. Right, yes, but it's not in canonical form. Why it's not in canonical form? Because we have a missing variable here. There is a variable A missing, and here the variable B missing, right? So this is, even though it's called standard form, and it's written as sum of products, but it's not canonical. The canonical form, there must be all of the variables. So even also when we talk about here, we see that this is 3 variables, but here there is a missing, here there is a missing variable. Okay, what do we need to do is, this is written in the standard representation. If we need to make it in canonical form, you know how to do it, which is basically the missing variable, add A plus A bar here. And here the missing variable, add B plus B bar. Okay? So in order to convert the standard form to canonical, the missing variable, as I mentioned earlier, add it to the terms. So as a result here, in order to do it as the missing terms in sum of products, so here we have A bar, B bar, C, plus, we will say A plus A bar times C bar, B C bar. Let me rewrite it. A plus A bar times B C bar, then plus A, then here we'll put B plus B bar, that's the missing variable, times C bar. Okay? Then it will be A bar B bar C plus A B C bar plus A bar B C bar plus A B C bar plus A B bar C bar. Then that's how we can convert it to canonical form. But keep in mind, look if there is any common variable after doing this simplification. If yes, keep in mind to make them 1. So you will see this one and this one are common. So you need to double check every time. So as a result, it will be A bar B bar C plus A B C bar plus A bar B C bar plus A B bar C bar. Don't forget, don't duplicate, don't let the terms duplicated. Make sure there are only 1, no repeated terms. Every time when we do this kind of simplification, make sure to do it. Now, how about if we have this function as written in max terms? How can we make sure to look at the missing variables? So in summary, x times x bar equal to 0. So we would say plus 0, this term plus 0. So how can we handle this? We can say A plus B plus C times, then I'm going to write it here in different color, times 0 plus B bar plus C bar times A bar plus, here is the missing variable is at location of 0, B, which is we will make it as 0, then plus C bar. Okay? Then we know that 0 is actually like A times A bar, and 0 is actually B times D bar, B bar. So we can substitute it here. So A plus B plus C times this 0, okay, the missing variable is A, then we'll make it A bar plus B bar plus C bar. Then let me make it the color universe. Plus B bar plus C bar, then times, here is A bar plus the missing variable here is B, then it will be B bar, then plus C bar. Now, there is a question, how to simplify these two? You can simplify, take it as a rule from the algebra, Boolean algebra. A bar plus B bar plus C bar can be simplified to be A plus B bar plus C bar plus A bar times. Let me do it again. I need to make sure I'm doing it in the right way. So it will be like A plus B bar plus C bar times A bar, and I'm going to make it this in color, red color, times B bar plus C bar. So we see the difference is just make the multiplication, put A here, put A bar here. That's how we do the simplification. Take it as a rule. Then for the second term, which is A bar plus B bar, then plus C bar, it will be A bar plus B plus C bar times A bar plus, we'll put here B bar, then plus C bar, like this. Okay? Now you can substitute this here and here. So as a result, it will be A plus B plus C times A plus B bar plus C bar times A bar plus B bar plus C bar times A bar plus B plus C bar times A bar plus B bar plus C bar. Then we are done. So we have 1, 2, 3, 4, 5 terms. Now, double check. Is there any similarities or is there any common terms? You will see this and this are in common. Is there any other common terms? I don't think so. So we have two terms in common. So don't duplicate this. Let's rewrite it by removing the terms are in common. A plus B plus C, then times A plus B bar plus C bar, then the common terms, write only one of them. That common term, write only one. A bar plus B bar plus C bar, then A bar plus B plus C bar. And that's it. That's how we modify or how we do it using the algebra. Then we can make sure that how we can convert this to make this as 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1. This one will be as max terms as M0 times M3 times M7 times M5. Then you can do it in the truth table and so on. Any question? Okay, is this clear? Okay. Again, sum of products. The good part of sum of products, when we manipulate this into the terms, like it will be as AND gates with one OR. Right? That's what we talk about this in the past. So when you manipulate this function and using the AND terms, we can get an AND and OR gates, we can represent this. So sum of product form, it can be into two representations. We have canonical form, we have any other simple forms. So sum of products is a general name, canonical form is part of it. How can we understand this is a canonical form or not? Look at this example. This example, this one, is written in sum of products, but not canonical. Why is not canonical? Because each term does not include all of the variables. So the first term, ABC, the second term, only BC. So it's not on the standard or the canonical form. However, this one is sum of products and canonical. Okay? So when you use sometimes the non-canonical form, again, this means we can, or sometimes the canonical form might include a larger number of gates or larger complexity than the non-canonical. This is the drawbacks of this. Even though that we're making standard, making it unique, but this is a drawback of it. So when we plot this function, we can do this function, for example, x prime z plus xy bar. We can make it using the non-canonical form, which is the sum of products. It will be still the same way and or, but again, it's not in the canonical. It's not as simple. Okay. Now, counting Boolean function, the good parts when we're using min terms or max terms, they are unique. This is one of the advantages, which is unique min terms or max terms. They are unique representations. How many Boolean functions can exist or we can achieve in how many possibilities functions using the variables? It will be, there are different combinations to make them. So even though that in order to determine the number of min terms or number of min terms or number of max terms, there will be as 2 power number of variables. So in 2 variables, it will be 2 power 2, it will be 4 min terms. So the range was between 0 to 3. and 3 variables, it was 2 power 3, then it will be 8, therefore from 0 to 7. 4 variables, 2 power 4, there will be 16 min-terms, they're the range from 0 to 15. Okay, do you agree with me? Now, how many possibilities for creating a function? What do I mean by possibilities creating a function? Let's look at this table. How many functions I can achieve using 2 variables? You will see I can make it 0, 0, 0. I can make another function 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and so on. So in order to create, or how many possibilities or how many functions I can achieve depending on the number of number of variables. So when we have 2 variables, we can achieve 16 functions. We can achieve 16 functions for 2 variables. How we can find this number? Basically, you can find it using 2 power 2 power n. This is how many combinations or how many possibilities. So the number of min-terms, again, 2 power 2, that's how we find it here. And 2 power 2 power n, such that n is the number of variables. So when we have 2 variables, it will be 2 power 2 power 2. 2 power 2 is 4, it will be 2 power 4, this will be 16. When we have 3 variables, it will be 2 power 2 power 3, which is going to be 2 power 8. 2 power 3, 8. Yes, 2 power 8, how much? 2 power 3, 8. Then power 4, 16. Power 5, 32. Power 6, 64. Power 7, 128, 256. 256, and so on. So when we have 3 variables, there is 256 possibilities functions to be created. So now we are testing our code ability. So when we have 2 variables, we are limited to do only 16 different functions. When we have 3 variables, we are limited to make 256, and so on. That's why, again, why we see the systems like 8-bit systems, then 16-bit systems, 32-bit systems, 64-bit systems. So the largest number, which means the largest number of variables, creates the largest number of possibilities of creating a functions, then we have a larger ability for creating a good software. That's why in old times, in 80s, 90s, the softwares were very basic, very simple. But right now we are going more complicated and so on, because we can make our code or our capability to be larger and larger and so on. Okay, so this table also summarizes what's the job of these 16 functions. What are their jobs? Or what's the equivalent circuits, the equivalent algebra, Boolean algebra on it after making the simplification. So the first function, f equals 0, means null, which means whatever you give any input, the output is every time 0. The second function is basically an AND. After making the simplification, it will be as AND. The second one will be as division, or we call it inhibition x, but not y. And there is the third one, which is f equal to x, only related to operator x, then and so on. X bar y, which means x y but not x, so there is then here is y, then there is exclusive or, then or, exclusive nor, then what else? This is, we call it xy plus x bar, y bar, this is called equivalence. Then we have y bar, x y bar plus y bar, we call it implication. We have a complement, x bar plus y, another implication. Then xy, all bar, which is NAND. Then f equal 1, which is identity, it gives us 1, no matter what's the outputs. So all of this is just like for your information. Then like with these 2 variables, we can create this amount. How about if it is more complicated, like 3 variables? We cannot make a table with 256 possibilities, but it will be more complicated than that. So there are here 16 possibilities, because again, it's 2 power 2 power 2. So you should be aware of this rule, like if we have 4 variables, how much will it be? 2 power 2 power 4, and so on. Just 2 power 2 power n is the number of variables. Any questions? Okay. Now here is the other part, or the other half of today's lecture, which is how to minimize this. So let's recall in today's lecture, or in this course, what we discussed so far. At the beginning of this class, I mentioned about the binary, hexadecimal, decimal. Then I mentioned about how to make the conversion. After that, I mentioned about the codes like BCD, Unicode, ASCII code, all of these codes. I mentioned that's how the computer understands them. After that, I go through the logic gates like AND, OR, exclusive OR, NAND, and so on. And I discussed what's the physical hardware. The physical hardware are based on NAND gates and NOR gates with NOT gates. Those are the physical components. Then I mentioned about how to make the program is basically to convert the variables or the written or the written program to be as variables like x and y and z, and these variables we donate them, or we make them in as a Boolean function, and that function sometimes it will be very large, very complicated. We need to simplify it. So we simplified this using Boolean algebra, using the postulates, using the theorems, using the results, so using different theorems. And we realized that dealing with this will be tough, maybe will not be unique. After that, we tried to look for a way to make a uniqueness. So my representation will be the same as yours, the same will be as other designers. Then we found that canonical forms are a great way to represent this because they will be unique, even though they are not minimizing the logic gates, but they are unique. Now, the next step is how to make them minimized. Because again, I mentioned canonical form does not mean they are unique. So in the past, we used to look at the function, use the postulates, the theorems to minimize it to get the final expression. Right? That was in the past. Now our target is to look at the function, convert this to canonical form. Now it's not minimized. What should I do? The next step is to minimize it. So now we will continue on it. So we will avoid using Boolean algebra. We will convert any function to canonical form or dual canonical form. Then after that, do the minimization. That's it. That's our targets. That's why we are learning canonical forms. We are learning canonical forms first to make it unique. After that, let's make the simplification. So we can standardize our answers again. So instead of applying some theorems that will like cause a lot of headache, they will not be hard to program, while canonical form can be easy to program. Canonical form can be easy to handle. So everyone know how to convert any function to canonical form. So the next step is to minimize it. So minimizing this will be much easier. So how can we minimize it? We can minimize it using something called Carnot maps or K-maps. So let's start, look at these slides. So in the chips, even though that we have millions of gates, but our target when we have any large program is to make these gates as low as possible, especially when we are dealing with very complicated programs. So this will take millions or millions, let me say, million of gates or thousands of gates, 100,000 of gates. So we need to reduce it. If we can reduce it as much as possible, we can save energy, we can save cost. How about if I'm building a product, if I'm making a product and make a production line, even though if I figure a way to reduce the number of gates 10%, this will be a great benefit. Maybe I can save thousands of dollars because of my program or the way that I realized that I can make it lower number of gates, I can reduce the number of gates, then I can reduce the cost, reduce the usage of chips, IC, reduce the usage of power, reduce the heat will be dissipated into the electrical board and make the device smaller and smaller. So it's very more convenient to make a minimization. So dealing only converting the system to canonical forms as a standalone, this is not enough. Even like make it as canonical system, we make it unique, but we miss the part of making minimize. So we're spending too much time, a lot of time, a lot of effort, or a lot of money on it. Therefore, we are in need to minimize these gates. So saving 1 gate in a memory cell pays off. So even 1 gate, if you figure out to save 1 gate, this is still a great benefit. So what's the criteria of minimization? What should we minimize? Should we minimize the product terms? Or should we minimize the logic operation? Should we minimize the variables? Should we minimize the wires? What should we minimize? Our target is to minimize the number of gates. That's our target. The usage of number of gates. So we can use a lower amount of chips or IC. We can reduce the lower amounts as possible. That's our targets. Even though when we are using the lower amount of this means we are saving more money. We are making it faster. So we'll make it faster, less cost, less energy, and even less complicated. That's why we're looking for simplification. That's why when we tried Boolean algebra, we spent a lot of time, we spent hard time on it, because we need to make it more, to save more money. How we do the minimization? That's the question now. How do we minimize this? Look at this function. How many gates do we have? You can look here. How many gates? Here, and, this is and, this is and, this is and. So we have 4 and, right? Using canonical form, this is in canonical form. How many or do we have? 3 or. Do you think can we make them in 1 or? Yes, we can have 1 or. Right? So we have 5 gates actually, 4 ands and 1 or. Actually, this function, if we use algebraic, Boolean algebra, we will realize that we can make a shortcut. So it will be like this: B, C bar plus A, B bar. If we simplify it using Boolean algebra. How many gates do we have? Do we need? We need 2 here, we need here 1 and, we need that, so we need to have 2 ands. Then we need to have how many ors? 1 or. So as a result, we need 3 gates. Here, in the past, canonical forms, you need to use 5 gates. So we can say that, simplifying this worth it. Let's assume that I need to build 1 million device in using this function. So if I need to build 1 million using 5 gates, I need 5 million gates. By using 3 gates, I need 2 million gates. 3 million gates. So the total net, I'm saving 2 million gates here. Let's imagine that each gate's worth maybe 10 cents. So I'm saving 1 million times 10 over 100. So I'm saving around $100,000 if I use just this small shortcuts. So does it worth to make the minimization? Yes, it's worth. How do you do it? We can make it use, it's called Carnot maps, K-maps. So if we need to simplify it using the Boolean algebra, you can, of course, but it's not recommended because it will take a lot of time, a lot of effort, and we cannot guarantee you will get the simplest one, especially if you are dealing with 5 variables or 4 variables Boolean algebra or Boolean function. How can you handle it? In the past, we used to deal with 3 variables and it was very hard. How about 4 variables? So how about 5 variables? What shall we do? And the good part about Carnot maps representation, we can make it as reducing the number of, or we can make it as a program actually. We can create a software that can make this simplification for me without using my hand. So just put the inputs and it will give you the final formula, and that's it. Which is great. So you can actually Google it, you can find any kernel maps function, so it can able to handle it. There is a function using MATLAB. It can be using, I think C language. Maybe in Python you will see it as well. So there will be a function, built-in function. It's already been open source in the internet, so you can look for how to do kernel maps using the software. You will see it will ask you to insert the min-terms. Just insert the min-terms, and the answer will be given. But it's not like to give you the whole function. You need to convert this function to canonical form. After that, enter the min-terms on it, then it will be counted. So here in this course, we will talk about how to deal with kernel maps as handwritten, like not using the softwares. It's super easy and easy to follow. So kernel maps, we will make it a shortcut as k-maps, and it's actually a graphical representation of Boolean function. So basically, kernel maps we need to create as a table. We call it kernel maps table. So this table will contain some squares, and these squares will be depending on the number of min-terms. So the number of squares were equal to the number of min-terms. So each square will be located, min-term located. Most likely kernel maps will be built on or based on min-terms. We will not use max terms. Max terms, if you want to use it, you can use it, but I don't prefer. I prefer to use the min-terms to make it our standard. So one map cell corresponds to min-terms or max terms. How do we do the cells? So there is one way, or there's two representations of doing it. So we have representation like we call it the two variable maps. Let's talk about two variable maps. We can make x1 here, x2 here. So we will make this is 0, this is 1, this is 0, this is 1. Then here m0, m1, m2, m3. Start row by row. There is another way to represent this. Flip, make x2 here, x1 here. Then we will make it column by column. 0, 1, 2, 3. In these notes, in my notes, I'm using this. In the textbook, they are using this. They are using this. So there are different on parts. When I prepare the notes, I prepare it in a way that, like when I was learning the digital logic course, we used to deal with this one. But I realized after I prepared the notes, okay, this is different, which is what we see in the textbook. So I don't want you to get confused. So I'll try my best whenever we will deal with the one that we will use in the textbook. So we will use this. So you will see some corrections when I deal with kernel maps, basically because I want you to use only one system, which is the one in the textbook. Okay? So basically how we do counting, basically we have 4 variables. We will say, we have 2 variables, then we have 4 cells. So we can say this is x2, this is x1, here is 0, 1, here is 0, 1. Then the locations, this is equivalent to 0, 0, this is equivalent to 1, 0, this is equivalent to 0, 1, this is equivalent to 1, 1. So because we know the variables, this is x1, x2, that's how we deal with it. x1, x2, x1, 0, 0, x1, x2, x1, 1, then x2, 0. Okay? Understood? Then, in terms of like the min terms, this is equivalent to, as a logic, so min term 0. This is equivalent to min term 1. This is equivalent to min term 2. This is equivalent to min term 3. Sometimes you don't need to manipulate it like this. You can memorize it like this way. This is x2, this is x1, then 0, 1, 2, 3. I'm sorry, 0, 1, 2, 3, like this. Like starts column by column. Okay? Now, how to represent the functions like to represent these functions. Let's assume we have the following truth table. Let's forget about this because this is used different representation than mine. That's the way that I told you. So let's assume that we have x, y. Here is function fa. Here is function fb. We have two functions. So this is 0, 0, 0, 1, 1, 0, 1, 1. Let's assume fa as 0, 0, 0, 1, fb as 0, 1, 1, 1. Now we need to simplify this or like write this in a kernel map. How can we write this in kernel map? Keep in mind, write the corresponding min terms. This is equivalent to m0, this is equivalent to m1, this is equivalent to m2, this is equivalent to m3. Okay? Now we have two functions, so we need to make two kernel maps. Each function has its own kernel maps. This function here. So I'm going to call this is y, here is x, 0, 1, 0, 1, this is 0, 1, 2, 3. This is for f1. For f2, I'm going to plot the same. This is y, this is x. This is 0, 1, 0, 1. So here is 0, 1, 2, 3. This is f2. Now look at the location of 1s. In f1, the location of 1 is only located at m3. So we will put 1 at m3. In f2, the location of 1 is located at 1, 2, 3. So here is 1, 2, 3. Okay? Now, how to make the simplification? To make the simplification, to find like how to find the function, each variable, look at the location of it. So we have here is 1. 1, this one is located between this one and this one. So this we can call it y, this is y, here is, I'm sorry, here is x, here is x, here is y. While the 0 will be x bar, here is will be y bar. This will be x bar, this will be y bar. Okay? Do you agree with me in this? Wherever there is 1, this will be the number, or I'm sorry, the variable without bar. Whenever there is 0, the variable with bar. Okay? So look at the 1. It's located between x and y. Therefore, f1 equal to xy. Because between x and y. Okay. Now, how to make the simplification using the other function? So kernel maps, in order to do the simplification, we can look at two adjacent blocks and combine them as one variable. Here, we can group 2 or group 4. So you need to group the first start with group 4. Can you group all of these 4 together? Or no, because we have only 3. I mean, we cannot group this because we have a missing variable here, right? We cannot group this 4. So the next step, try to group 4. Can we group 4 as a box? Group 2? Yes, we can group these 2 together, right? Okay. Now, when you look at this first circle, there is still 1 left here. So we can group it alone, but still this is not the simplest way. We can make some overlaps. Like, we can group the other 2 together. That's fine to do the overlaps. Okay? So now do you agree with me how do we do the grouping? Okay. The only group that can be as a box, so we can group each 4. If you cannot, group each 2. If you cannot, group 1. So that's the way that we are thinking. So we have 2 groups. So by look at this group and this group, look at the first group. I'm going to make it here number 1. Look at here number 2. Look at the box number 1. It's located between x. Then the other side located at y bar and y's. Is that right? It looks like x plus or x times y plus y bar. Y plus y bar is 1. It will be x times 1. So it will be x. So as a result, we will not do every time y plus y bar. Look at this box. It's located at x. Then it will be x. Look at this box. Box number 2 is located at y. Because the other part is x bar, this part is x, then they will be cancelled each other, then we will be y. So as a result, F2 will be x, which is box number 1, plus the other box, which is box number 2, which is y. Then that's it. So as a result, we are simplifying the function from being like the original using the canonical form. This function using the canonical form was I think x y bar plus xy plus x bar y. This is F2 in canonical form. While F2, after simplification, it's x plus y. Then as a result, instead of using algebra, Boolean algebra, we can get F2 x plus y using Carnot maps. That's the overall idea of Carnot maps. So actually, you can mix like some theorems, like take x as a common factor, it will be y plus y bar, then it will be 1. Then you need to make sure that x bar plus y, take some factors to make it another, to make it as x plus y. So again, as a result, we will get x plus y using Carnot maps, so the problem will be much easier, other than using the theorems or using the postulates or the other stuff. So we have 2 ways to deal with it, using Boolean algebra or using Carnot maps. Okay, any question? Okay. So the 2 variable maps, you need to look for, in summary, 2 adjacent cells, or maybe 4 if it can be required. So any 2 adjacent for 2 maps, it will include 1 variable, like what we did here. It will include 1 variable. Then, which will be appears as shown here. So for example, if Carnot map, here is x2, x1. If there is no element at all, this means f will be 0. If Carnot map, if all of these elements are 1, then f will be 1. Okay? The remaining, you need to look at the function and know how to do it. Let's consider this example. This example is being solved using the different method, but here I have different one because in the textbook has different x2 and x1 locations. So, I apologize about this, but let me do it in the textbook method, which is the method that we will use it. Do the Carnot maps. Don't forget to draw the table. So here is x2, here is x1. So here is 0, 1, 0, 1. Then look at this function. We have m0, m1, m2. m0, m1, m2. Or you can look at the original function. F x1, x2 is equal to x1 bar x2 plus x1 bar x2 bar plus x1 x2 bar. This is equivalent to 1 0, this is equivalent to 0 0, This is equivalent to 0, 1. Therefore, it will be M0 plus M1 plus M2. This is canonical form. Or you can say it's M0, 1, 2. Then M0, 1, 2, those are the locations of ones. Therefore, according to canonical form, kernel maps, this is 0, 1, 2, 3. Then the location of ones will be, here is 1 at, let me write it in different color. Here is 1. Then at 1, here is 1. Then at 2, here is 1. Okay? Now we need to group. Let's group each 2 together. We cannot group the 4. That's because there is a missing here. So let's group each 2. We can make our first group here by grouping these 2. The second option or the second way is to group these 2. Okay? And remember, when we deal with kernel maps, this is because at 1, so here is x1, here at 1, here is x2, whereas whenever there is at 0, it will be x bar, x bar. So the first group set is located between x1 and x1 bar. Therefore, neglect this x1. Look at here. It will be at x2. So the red color, it will be at x2 bar. Why? Again, look at it. Here is x2. So this position is x2 bar. Here is x1 bar. Here is x2 bar. So this one located at x1 bar. This one located at x1. This one is located at x2 bar. Then we are not using it. Don't use it. So it will be at x2 bar. How about the purple one? The purple one, it's located between x2 bar and the other x2 bar here, and still x2. While look, I think this is x1 bar. Yeah, x1 bar, and this one x1 bar pi. For regarding to the rows, this is x2 bar. This is x2. So we will use only the x1 bar here. As a result, the function f will be x2 bar plus x1 bar. Then this is the minimization for the function. Now here I'm over explaining this, but you need to practice very well so you can do it in a simple way and shorter time. Now, how to deal with kernel maps using 3 variables. This will be our next lecture topic. Do you have any questions about 2 variables? Okay. So that's it for today's lecture. Next lecture we will go on kernel maps 3 variables. Thank you.